In this video, we're going to talk about the first derivative and how it affects the graph of a function. So we call this increasing and decreasing. So I call them functions, and that leads to the investigation of critical numbers. So we already know that the first derivative tells us the slope of the curve. But it actually tells us a bit more information, and I've used the words increasing and decreasing already because intuitively you probably understand them because we use these in English all the time, and you know what they mean. They mean the same thing here, so probably you weren't confused when I used them in the past, but now we're going to define them formally. So if f is a function defined on some interval, where the interval has any two numbers, x1 and x2, we say that f is increasing on the interval if f of x1 is less than f of x2 whenever x1 is less than x2. So what that means is that the y values are getting bigger as the x values get bigger. Okay, so if I draw you a picture over here, okay, so maybe my interval is, okay, like that. Maybe I have x1 is here and maybe x2 is over here, so x1 is less than x2. What this says is that my function, so the y value of x1 is less than the y value of x2. Okay, so my curve is doing something like this, and it does it on the whole interval, so it doesn't matter which x1 and x2 I pick in the interval, but the y value of the smaller one is always smaller than the y value of the bigger one. So what this means is that the graph moves up to the right on the interval. Okay, so on the entire interval. So if f is decreasing on the interval, then we say that f of x1 is bigger than f of x2 whenever x1 is less than x2. Okay, so in that case, we're just going the other way. So the picture, I'm not going to do I this time, but let's say that x1 and x2, so the y value for x1 is actually bigger than the y value for x2. Okay, so you might get some shape like that on the interval. So here you're going down to the right. Okay, we usually move from the left to the right when we talk about slopes or increasing, decreasing. Okay, so just less formally, so f is increasing if the graph moves up, okay, as we go from left to right. Over the interval. Okay, it's going to be decreasing if the graph moves down as we go the same way. Okay, so we're always moving left to the right. Maybe I'll just highlight. So we have the increasing if you're going up, okay, and the decreasing if you're going down, okay, as you go to the right. Some examples. Now the ones I'm going to give, these are always increasing or always decreasing. So I'm going to do some increasing ones first. Okay, so you could have a function like the exponential functions. Okay, so those are always increasing, well, with the a that's bigger than 1. So this would be increasing. You could actually have something that looks like that as well. This is actually less intuitive, maybe, that it's increasing because of the shape, but the y values are still getting bigger as we move to the right. Now, an easier example that we're already familiar with is a line. Okay, so a linear function, okay, so all of these are increasing on the whole x-plane. So they're increasing always. So as we move to the right, they're always getting bigger. And now this linear one, notice that the slope here is positive. Okay, so when you have a line, if it has a slope positive, that means it's going to go up to the right, which is what we say for increasing. Okay, now for decreasing, you can have sort of similar shapes. Okay, so maybe I have an exponential with a value that is between 0 and 1. Okay, that would be decreasing on the entire interval. Or I could have a shape like that. This is also decreasing. Okay, and again with the linear functions, if I have a negative slope, then my function is decreasing. Okay, so these three are all decreasing on the entire interval. Okay, and this linear one has a slope that's negative. Okay, that's going to mean something in a minute here. So let's look at a graph. Okay, so I've drawn this graph for you. We want to determine on which intervals is it increasing or decreasing. So what we're going to do, I usually just start from the left and think about moving right. Okay, so I'm going to just make it. Okay, so we're going to list intervals that are increasing, intervals that are decreasing, and it's possible that we might have some intervals that are neither. So that means that they're actually constant. Okay, so those are the three things that can happen. Now, as we go from negative infinity until -7, notice that our y values are getting bigger. Okay, so that means that we're increasing, so that interval is going to be in our increasing interval. Okay, from negative infinity to -7. Now, after -7, the x value, our function decreases, right? The y values are getting smaller as I continue to the right until I get to the x value -3. So I'm going to add that to my decreasing intervals. Okay, now this interval between -3 and 1, the y values are always 2. Okay, so they're not changing, they're not increasing, they're not decreasing, they're staying the same. So here is actually a constant interval from -3 to 1. Now after 1, so from 1 until 4, the graph drops down further. Okay, so that means that we're decreasing, so we're decreasing from -7 to -3, and then we do this union symbol to mean this other interval as well. So the interval from 1 to 4. And then from 4 to 6, the graph goes up. Okay, so that's an increasing interval. Okay, and then from 6 to infinity, the graph is going down. Now, even though we approach an asymptote here, we're always getting closer and closer to the asymptote, so we keep decreasing forever. Okay, so then decreasing also from 6 to infinity. So it is fairly straightforward to tell when you're increasing and decreasing when you have a graph. What about if you didn't have a graph? Okay, so what do we notice about the places where the function is increasing? So in particular, how would we describe the slopes when the function is increasing? So let's just take a few points in these intervals, okay, and we'll think about the slopes. So I'm going to draw some tangent lines. Okay, so when I'm, say, at -8, okay, my function is increasing. And when I'm down here, okay, my function is increasing. When I'm up here, I still say it's increasing. Okay, when I'm down here, it's increasing. So what do all these slopes have in common? Well, it looks like they're all positive. Okay, and that's exactly what happens. So when the function is increasing, increasing, we get a positive tangent line slope. Okay, now when the function is decreasing, I'm going to use a different color here. So let's say when I'm here, okay, that's what my slope looks like. Okay, and I'm here, it kind of looks similar. When I'm down here, kind of looks like that. Again, all these slopes are negative, right? They're all slanting down to the right. Okay, so when they were decreasing, we get negative slopes from our tangent lines. Now, what does this mean for the derivative? Remember, the derivative is the slope of the tangent. So when we're increasing, we must have a derivative that's positive. When we're decreasing, we must have a derivative that's negative. Okay, this is how we're going to test for increasing and decreasing when we don't have the graph in front of us. So, suppose a function has a derivative at each point in an interval I. Okay, then for each x and I, then if for each x and I, so if the derivative for each x is positive for every x in the interval I, we say that f is increasing on I. If the derivative is always negative, then we say that the function is decreasing on our interval. And if our function is always 0, that means that our graph is flat there, so we would say f is constant on I. Okay, so let me just draw. So increasing means you're going like that, decreasing like that, constant, you're flat. Okay, so we're going to use these symbols to indicate increasing, decreasing, so we don't have to write it all the time. So it's going to be important to determine where the function derivative is positive or negative. Okay, so we want to know when can it change signs. So we talked about this a little bit in a previous video. But the derivative can change signs, so go from positive to negative or negative to positive, if there is an x value c such that, so either we go through a 0, okay, so we might go through a 0, so then we could switch, right? The derivative can move from negative to positive or positive to negative, or we could have a derivative that doesn't exist. Because then maybe there's a jump in the derivative graph or something, okay? Something weird could happen there. So these places are important, and we call these x values critical numbers. Okay, so the definition, the critical numbers of a function f are the numbers c, now it's important that they're in the domain, okay, for which either of these things happen. So f prime of c is equal to 0, or f prime of c does not exist. Okay, those are our critical points, but they need to be in the domain. Okay, so they're in the domain of f. Now so those are critical numbers. Okay, so the critical number is the x value. But we also have this idea of critical point. Okay, so the x value is a critical number, and the y value is what goes with it. Okay, so this is the point c f of c, where c is a critical number. Okay, so the critical numbers are x values where the derivative can switch signs. There are other places where the derivative could switch signs, and that's when the function doesn't exist. Okay, so what this means is the x values that are not in the domain. Of our function. Now, these cannot be critical numbers because they're not in a domain. The critical numbers are always in the domain. These ones are not. So these are the things we want to watch out for. Okay, but what this means is that for any points, but for in the intervals between any of these 2 points, the derivative has to be all positive or all negative. Okay, so what we're going to do is find these points, split up the domain using these points, and then we just need to test in the intervals. Okay, so let me just outline that procedure for you, and then we'll do an example. So to determine whether a function is increasing or decreasing, what we want to do first is find all critical numbers. Okay, and places where the function does not exist. Okay, so remember the critical numbers are when the derivative equals 0 or the derivative is undefined. Okay, now these other ones, this is where the x values, where the function does not exist. Okay, so they could be like vertical asymptotes, for instance. And we know that when you have a vertical asymptote in the graph, that the graph could look very different on each side. Okay, so that means the derivative could change there as well. So we find all these numbers, and then what we do is place these numbers on a number line. Okay, so what this is going to do, this will split the domain of our function into sub-intervals, or maybe I'll just say intervals. Okay, into smaller intervals where the function is either increasing, decreasing, or constant. Oops. Well, actually, we're going to take all the zeros, so actually just increasing or decreasing. Okay, so then what we have to do is choose an x value in each interval and plug it into the derivative to see if it's positive or negative. Okay, so now, and then we can apply the test. So if the point you chose, so if f of x, f prime of x is positive, okay, that means that f is increasing on that interval. And if the point you plugged in is negative, then f is decreasing on that interval. Okay, so you just apply the test. So that's the idea. Okay, so we want to take the derivative, find its critical numbers, so set it equal to 0, figure out what x values make it 0, what x values make it not exist. Make sure to think about the domain of f. Okay, so those points that are not in the domain should also be included. Place these numbers on a number line. Pick an x value in each interval. Plug it into the derivative to see if the derivative is positive or negative. and then use the test to tell if that means it's increasing or decreasing. Okay, so let's just do a couple of examples here. So suppose my g of x is 12x to the 4 minus 12x to the 3. Okay, so first of all, I'm going to say the domain, this is a polynomial, so the domain is all real numbers. So there's no x values where f of x does not exist. Okay, we don't have any of that type. So we want to find the critical numbers, so we take the derivative, so that's going to be 12 times 4, so 48x cubed, minus 12 times 3 is 36x squared. Okay, I'm going to factor this a bit so I can pull out 12x squared, and I'm left with 4x minus 3. Okay, so that's my derivative. So now I want to find my critical numbers, so I'm going to set the derivative equal to 0. Okay, we're going to be doing this a lot. So the derivative equals 0. When does that happen? Well, 12x squared times 4x minus 3 should equal 0. Now I have two things that are multiplied together equaling 0. That means one of them has to be 0. So 12x squared is equal to 0, or 4x minus 3 is equal to 0. Okay, so that means that x equals 0, or x equals 3 over 4. Okay, so those are two critical numbers. Oops. Okay, now we also want to check, where does the derivative not exist? Okay, so we need to check both of these things, but g prime of x is a polynomial. Oops. Which means that it always exists. Okay, so there's no critical numbers of that type. Okay, so these are our only two critical numbers. They're both in the domain, because the domain is everything. Okay, so they're critical numbers. So now we put them on a number line. Okay, so in the right order. Okay, so I'm going to have a 0 and a 3 over 4. Okay, now those are going to split my domain into, see, I have 3 intervals. Okay, in each of these intervals, the function is either increasing or decreasing. So all I have to do is check a point in each interval. Okay, so let's say something less than 0. Okay, maybe I pick -1. You can pick whatever you want. Okay, so now I'm going to plug in -1 into my derivative. Now again, you can plug into this form or this form. I generally prefer to use the factored form if I have it, but you can use whatever you'd like. So it's 12 times -1 squared times 4 times -1, minus 3. Okay, so this is -1 squared is +1, so this is just 12 times -4 times -3, or sorry, minus -3, minus 3, so -7. Now I don't even care what this number is. Okay, I know that it's negative because it's a positive times a negative. Now I want to do the same thing in the next interval, but I want to pick something between 0 and 3/4. So maybe like 1/2 might be a good number. So g prime of 1/2 is going to be 12 times 1/2 squared times 4 times 1/2 minus 3. So this is 12 times 1/4 times 2 minus 3 is -1. Okay, so notice I have a positive times a positive times a negative. Okay, so I only have one negative. This is going to be a negative number. Again, I don't actually care what it is. It's going to be -3, but I don't actually care. I only care if it's positive or if it's negative. Now I want to test something bigger than 3/4. Okay, maybe 1. So So I plug it into the derivative. So it's 12 times 1 squared times 4 times 1 minus 3. So this is going to be 12 times 1 times 1. Okay, we know this is 12, which is a positive number. Okay, so that means that when I'm less than 0, no matter what I pick, my derivative is going to be negative. When I'm between 0 and 3/4, no matter what I pick, my derivative is going to be 0. Okay, so if you don't believe me, try picking a different number. Plug it in, see what happens. So now we want to use our test. If the derivative is negative, it means that the function is decreasing in that interval. So I'm just going to draw that with an arrow so we remember. So it's decreasing here. Negative means we're decreasing. Positive means we're increasing. Okay, so now I'm just going to write my summary here. Okay, so g of x is, so increasing, and we should give our answer an interval notation. So it's increasing when I'm bigger than 3/4. Okay, so on the interval from 3/4 to infinity. Okay, and it's decreasing on the interval from negative infinity to 0, and then 0 to 3/4. Now I split at 0. If you don't, that's not really a big deal. Technically, it's probably not decreasing at 0 because it's at 0, but it continues to decrease. So if you had written negative infinity to 3/4, that would be fine with me. I like to just keep all the intervals separate. But anyway, so that would be our answer. So now we found where it's increasing and decreasing. Okay, let's try one more. So here my function f of x is x minus 1 to the power 2/3. So this is actually, if you rewrite it, the cube root of x minus 1 squared. Okay, when I have a cube root, it doesn't matter what's on the inside. Okay, so here the domain, again, is negative infinity to infinity. So we don't have to worry about any places where f of x doesn't exist. Oh, and I just remembered that I wrote f of x up here. It should be g of x. Sorry about that. Okay, so there's no points where the f of x doesn't exist. So we take its derivative. So we bring the 2/3 down. It's going to be x minus 1 to the 2/3 minus 1, which is negative 1/3, times the derivative of the inside, which is just 1. Okay, now if I rewrite this, this is 2 divided by 3 cube root of x minus 1. Okay, so that's my derivative. Now what I want to do is set the derivative equal to 0. Okay, so when is my derivative equal to 0? Well, I need 2 over 3 times cube root of x minus 1 to equal 0. So when does that happen? Well, when you have a fraction equaling 0, it's actually when the numerator equals 0. So if the denominator equals 0, then it doesn't exist. And you could also think about timesing both sides by the denominator. Okay, so on the left side, it's going to cancel out. Okay, on the right side, 0 times anything is 0. So what we get is 2 equals 0. Okay, so this doesn't make sense. Okay, so that means there's no solutions here. So there's no x values in this example where the derivative equals 0. But it is useful to remember, if you have a fraction, okay, equaling 0, it has to be that the numerator is 0. Okay, and you don't want the denominator to be 0 at the same point. Okay, so there's nothing there. So now we want to know, where does the derivative not exist? Because we can also get critical numbers that way. So it's going to not exist when the denominator is 0. So that's when I get 3 cube root of x minus 1 is equal to 0. Okay, so that's when it's going to be when x minus 1 is 0, which is when x equals 1. Okay, so it turns out that this is our only critical number. Okay, so, and it's in the domain, I should say, because the domain is everything. So we make our number line. Okay, the domain is all real numbers, so we want to use the whole thing. And we only have to split at 1. Okay, so I test a point that's less than 1, maybe 0. Okay, so f prime of 0 is going to be 2 over 3 times the cube root of 0 minus 1. So this is 2 over 3 cube root of minus 1. The cube root of minus 1 is minus 1, so this is going to be negative 2/3. Okay, so in particular it's negative. If I check something bigger than 1, maybe 2, f prime of 2 is going to be 2 over 3 times the cube root of 2 minus 1. So that's the cube root of 1. So this is going to be positive 2/3. So in particular, it's positive. So in the first interval, we have a negative derivative, so we're decreasing. And then in the second, after 1, we're going to be increasing. Okay, so we would write f of x is increasing on the interval from 1 to infinity and decreasing on the interval from negative infinity to 1. Okay, so those are all the places where we're either increasing or decreasing.